In this tutorial, I'm going to show you how to use a truth table to assess the validity of an argument. So basically, we will continue the same process that we have learned in the past for constructing a truth table for multiple different propositions. Only the difference is, in this case, we'll construct the truth table so that we can see the truth values of the premise or premises and the conclusion, and then we'll use the truth table to assess validity by interpreting the results of the truth table in light of the definition of validity, which is, if the premises were true, the conclusion cannot be false. So the theory behind this is, since the truth table includes every possible combination of inputs, we will be able to see the complete behavior of the premises and the conclusion. And if there's no line in the truth table that shows that the premises can be true and the conclusion can be false, then it can't break that definition of validity. If the premises were true, the conclusion cannot be false. Okay, so let me illustrate this with an example. So let's start with an argument. P implies Q and R. The second premise will be P, and our conclusion will be R. So we're going to construct a truth table for this argument. So we'll start with P implies Q and R. That's our first premise. The second premise is P, and of course the conclusion is R. Okay, so now I'll draw double lines here between the premises and the conclusion. Okay, lines here, a double line between the first premise and the input values. So now you'll notice in this argument we have three variables, and each variable is, well, P is used twice, Q appears only once, and R appears twice, but there are three distinct variables. So since there are three, then our number of rows is 2 to the third power, which is 2 times 2 times 2, which is 8. So we need 8 rows. So here we go, 1, 2, 3, 4 rows, and then I'll use a line to keep us organized, and 4 more rows. All right, so for the variables, P, Q, and R, we're going to construct the inputs, starting with P, and we'll alternate by ones, true, false, true, false. True, false, true, false. That gives us our 8 rows. All right, now for Q, we double the alternating factor, so we have true, true, false, false, true, true, false, false. And for R, we double again, so we're going to have true, 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 and false, 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 false. Okay, good. Now it's time to calculate the output values for each of these expressions. So let's start with the most complex expression. This is the first premise. So we have our major operator here. It branches two ways. There's no operator on the P side, but over here we have a level 2 operator. So we'll do the level 2 operator first. And again, just to remind you, we're going to pick up truth values for each row from the inputs, use the operator to calculate the output. So we'll get the value of Q and R from the input, so that for the first row that's true and true, so true and true makes true. True and true makes true. For the second row, false and true makes false. False and true makes false. For the fifth row, true and false makes false. True and false makes false. False and false makes false. False and false makes false. Okay, so that's the value for the level 2 operator. Now we'll feed this value up to the level 1 operator and pick up the value for P from the input. So for the first row, P is true, and this expression on the other side of the implication is true. So true implies true is true. False implies true is true. True implies false is false. False implies false is true. True implies false is false. False implies false is true. True implies false is false. And false implies false is true. So that gives us, excuse me, that gives us the output now for the overall expression right here. And that's the output that we're going to use to interpret the truth table. All right, so now let's calculate, in quotes, the output for P. So since there is no operator in this premise, then nothing happens to the input value. So we just basically draw the input values from our input columns, just like this. And same for R. There is no operator in the conclusion, so it will be whatever the input value is for R. So true, 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 false, 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 and false. Now we've got the truth table finished, meaning we have the output values for the premises and we have the output value for the conclusion for every possible trio of input values, which we do row by row. So now it's time to interpret the result. So what we're going to look at is this part of the truth table, the premises and the conclusion. And we're going to ask the question, is it possible for the premises to be true when the conclusion is false? Now, we could do this row by row. If you look at the first row, for instance, you will see that for the first row, the first premise is true, the second premise is true, and the conclusion is true. Obviously, when the conclusion is true, it can't violate the definition of validity, which is true premises, which is if the premises were true, the conclusion cannot be false. So it's more efficient to look at the places where we could have a violation, and that is the rows where we have a false conclusion. So look at those rows. In every case, so like for instance the fifth row, we don't have both premises true. We may have one true, but the other one is false. But notice, if one is true and one is false, it doesn't violate the definition of validity. So again, the definition of validity says if the premises were true, like all true, then the conclusion cannot be false. So for each of these rows, what we see is that there's a false premise, which means that in this whole truth table, there is no row in which we find that the premises are both true and the conclusion is false. So now, think about this. Since these inputs are all the inputs that could possibly be given to these three propositions, this means that it's impossible, meaning there is no situation in which the premises could ever be true and the conclusion false for this argument. And so, since it's impossible, we could say that this argument is valid, except not quite so fast. If you look at this truth table, you'll realize that what's actually present in the truth table is weirdly enough, a lack of evidence. It's a lack of evidence that the argument is invalid. So that means that if we were going to be technically precise, the assessment is that the argument is not invalid. Now you might be thinking, well, if an argument's not invalid, doesn't that mean it's valid? And the answer is it's a little more nuanced than that. If you go on and take a more advanced mathematical logic course, this is a topic that will come up. So for a variety of reasons, it's better for us to focus on what's technically true, and then we can go ahead and informally say that an argument is valid or invalid based on the truth table. So what's technically true? In this truth table, there is no row in which we can find true premises and a false conclusion. So technically that means the argument is not invalid. Informally, let's go ahead and say that arguments that are not invalid are valid. And if they're valid, then that means that we can give a formal proof of validity, which is the next unit. So this is an overview of how to use a truth table to assess validity. Essentially, you start with the argument. You lay out the argument as a truth table so that we can compare the values of the propositions that compose the argument based on exactly the same inputs. And then what we do at the end, when we've got all of the outputs calculated, is we look for a violation of the definition of validity, which is if the premises were true, the conclusion cannot be false. What this argument shows is that there is no row where the premises can be true and the conclusion false. So we pronounced it not invalid, or speaking informally, this argument is valid.